Hello, welcome back. And today we're going to do unit in physical optics technique number 5, which is a study in the rectangular aperture problem using the Fresnel techniques that we learned in the previous lecture. And this is a great little problem that helps us understand some fundamental things about diffraction, and we use it to get our knife edge result. So imagine if you have a perfectly shielded screen. On one side you put your source, and on the other side you put your observation. And where it hits this plane is actually the origin. And then you have a rectangular aperture, and we apply Kirchhoff boundary conditions, which says that the total field in this area right here inside the rectangle is going to be equal to the incident field, and it will be 0 everywhere on the screen. So these are approximate boundary conditions if you have a perfect absorbing screen or a metal screen. They're not dependent on polarization, so automatically we know there's a little bit of something off, and there turns out there will be something off and polarization dependent here along the edges of the screen. But this is a very helpful problem for studying, and it allows us to also introduce some constructs that we'll need later. So here's a little more formal description of what we're after. Here's our problem. Remember, what we started off with was the Kirchhoff-Helmholtz integral theorem from the previous lecture. And we modified it so that we had, of course, our Kirchhoff boundary conditions. Our other assumptions were the Fresnel approximations to the phase terms, which allows us to get much closer than we normally would in a regular solution. Usually when this is simplified in the Fraunhofer approximation or the far field approximation, the math gets a lot simpler and you get basically antenna patterns of screens. But this Fresnel approximation allows you to get much closer to the aperture and get a really good estimate of the field strength. Again, we're using scalar diffraction theory, which says that whatever the polarization is, that's what it's going to keep on doing. So whatever we transmitted, if we transmitted x hat, it will be x hat, y hat, it will be y hat. We'll see a little later in the course that this isn't a bad approximation. And if the scalar approximation with the Kirchhoff boundary conditions winds up being a happy medium between what would be parallel or perpendicular polarization, as we like to describe it. So this is our starting point. We derived this. We spent a couple lectures getting to this point. And then, to solve our aperture problem here, what I'm going to do, it's actually pretty simple. We'll just define rectangular limits of integration from y1 to y2 and from x1 to x2, and dx hat and dx prime and dy prime, those will be my variables of integration here. I'm also going to do something kind of sneaky, and that is by lining things up with the origin here. So I'm going to basically say my source point and my origin and my observation point are all on the same line. These are all collinear. And I can do that without loss of generality as long as I get to control the limits of the rectangle, right? If I find, for example, that I've set up the problem incorrectly, I have a rectangle here. Here's my origin. Here's a point of observation. Here's my source. And when I draw a straight line from observation to source, I find it should go intersect that plane right there. So I just need to do a change of variable to bring that point over to there and call that the origin. And then it, of course, adjusts my limits of integration, y2, y1 from here to here, and x1, x2. So this is like the famous part of the book when the instructor says, without loss of generality, we're going to make this change that really, really simplifies the math. Okay, so where do we go from here? We've got this rectangular aperture. And what we see is that we're going to get this nice exp to the minus jk r naught plus r term describing the phase propagation. There's going to be attenuation with respect to r naught and r, the distance from the source to the screen and from the screen to the point of observation, and the Fresnel phase integral over here. And this is a pretty wicked looking math problem unless you do a change of variable. So we're going to transform x prime into a change of variable involving u with this relationship, and I'm going to change y prime into this change of variable involving v through this relationship. And I won't bore you with the details, but if you calculate dx prime and dy prime, this is what it should look like. So let's go ahead, plug this into there. There's my limits of integration. I got a x prime cosine squared theta times this term. That's basically what I see, what I have as my first term in here. That's just a pi over 2 u squared. Again, this term I've chosen in such a way that leads me to substitute this as pi over 2 v squared. And when I adjust the limits of integration, now I've got this formula here. So what I would need to do is to substitute x1 and x2 to get my u1 and u2 limits. And then I'd have to do the same thing in y. So that part's a little bit tricky, but the remainder is actually pretty interesting. It leads to two basically identical formulas for the integral. An exp to the minus j pi over 2 u squared du, and then an exact same integral with the y limits, or the y related limits, with respect to v. And of course, we recognize that that complex exponential is really just cosine pi over 2 u squared minus j sine pi over 2 u squared, or v squared. And at this point, we have to invoke a special function. So it's fun. We get to learn a special function today if you haven't come across this one already. This is a peculiar form because you're integrating across a cosine or a sine function with a squared argument. So if you just think about how that is, cosine u squared would look something like this. It'd start out like a cosine, and it would be even, and then it would just go faster and faster and faster and faster in both directions. And integrating this thing is kind of a bear although we can make some approximations sometimes. But if you think about it, if the window of integration includes the part close to 0, I'll get a pretty big change. If my limit of integration occurs over here or over here, the window goes down the line where things get really, really fast, I actually wind up integrating something close to 0. Why is that? Because this thing is oscillating back and forth so quickly. If I move across a window over here, then I've got lots of up cycles, lots of tiny up cycles, and lots of tiny down cycles. The net result isn't going to be that big. Either way, positive or negative. Same with the sine wave. The sine wave would start out looking like a regular sine wave, and then very rapidly oscillate. And in fact, this would actually be even, right? Because you got a sine squared, so it wouldn't be odd. It's kind of confusing because the cosine and the sine, when you square the arguments, are both even functions, which means the indefinite integral of this thing with respect to u or v would be odd functions, both of them. Well, these happen so often in mathematics that we've kind of given them special names. These are the Fresnel cosine and sine integrals. Fresnel's integrals for sine and cosine. And we've got a lot of relationships that can apply to these. Okay, so let's keep going. The Fresnel integral functions. We define them exactly as we did in the previous thing with respect to sine and cosine, and one of the conventions is to give that function for the cosine a script C, only a script S. And here's what they look like when you graph them. Note here we're defining them as definite integrals from 0 to some value a. And because these are odd functions, if a is negative, it's just the exact same value as if it were positive with a minus sign in front of it. Here's what they look like. The solid line is cosine integral, the Fresnel cosine integral. And you see what happens. Starting at 0, you get 0. Goes up and up and up and up and up, and then you start to get that heavy, faster increasing oscillatory behavior. Same in the other direction. Now the sine integral starts out even slower, and then all of a sudden pops up again to a similar value and starts that increasing oscillatory behavior, and it's identical in that. Now, as a side note, these integrals, when you plot them parametrically with cosine integral on the horizontal axis and sine integral on the vertical axis, and you let that a parameter vary as the cosine and the sine trace coordinates on a Cartesian graph, you get a very famous structure called the spiral of Cornu. It's a beautiful spiral, and very interestingly, it spirals to this asymptotic value where ultimately, spiraling faster and faster and faster, cosine and sine hit the value positive 1/2, positive 1/2. And if you go the other direction, it spirals faster and faster, collapsing into the point negative 1/2. 1/2. So it's kind of a beautiful mathematical structure that comes out of the Fresnel integral, this peculiar spiral. Now, you may see this, an alternate way of expressing these solutions is as something called just a Fresnel integral function, which is defined with a complex exponential. See, it's almost identical, except two issues. We got an infinite limit at the top to a, whereas the cosine integral was from 1/2 to a. And we're doing both complex values at the same time, a cosine and a sine. So you can relate the two functions, the complex Fresnel integral and then the cosine and sine integral functions, through this relationship here. And here's a nice set of properties, if you ever need them, for the limiting behavior and the definitions of the integral. And if you ever get really bored, you can play around with these series definitions. So, now that we know all there is to know about the Fresnel integral function, let's plug this into our original problem. Here's my rectangular aperture of field, E or H. It's related to the initial amplitude of the field. And when we evaluate these at these limits, we can write these as cosine integral of u2 minus u1 and sine integral, this is the complex part, u2 plus u1, and likewise cosine integrals here, here, and here, sine integrals there for the v limits. And here's little relationships that you can use to translate the x limits and the y limits and regular meters to their corresponding u and v arguments. Now these are well tabulated functions. You can get them evaluated pretty easily in any mathematical package. And of course there's tons of tables out there that you can use to analyze them. It was interesting to know what happens. So what would happen if we let all the limits go to infinity? We stretch the rectangle in every possible direction so that it becomes extremely large. Well, look what happens in this formulation. First of all, I notice that the bottom denominator term is 2r0 plus r, so basically the total distance. And we said that whenever these functions get stretched to the limit, I get a 1/2 minus a 1/2 minus 1/2 minus j 1/2 plus a minus j 1/2. So if I evaluate that, that is 1 minus j. If I do the same thing with this limit with my infinite rectangle, I get a 1/2 minus 1 minus a minus 1/2 and then I get the same thing here, minus j 1/2, 1/2 plus j minus 1/2. So another 1 minus j. So if I multiply those two together, I get 1 minus 2j plus times g minus j times minus j. That's actually a minus 1. So I get minus 2j. Now I go back over here, I notice I have a j, a minus j times j. J times j is just positive 1, and then the 2's cancel. So what I'm left with is a field solution that looks a lot like just first free space propagation. exp to the minus jk, total distance between source point and observation point, divided by the distance traveled, just like a free space wave. Oh, it's always nice when that works out. Those kind of sanity checks are always very important. So, mull over that solution, because we're going to use it to do something very interesting involving a diffracting screen, a knife edge, at the next lecture.